Okay, here we're looking at chapter 6.6, and our essential question is how can you use a geometric sequence to describe a pattern? So here are our learning targets. The first one is identify geometric sequences. So we've worked with some sequences in the past. We worked with some arithmetic sequences. So now we're just looking at a different type of sequence. Our second learning target is extend and graph geometric sequences. And then finally, we're going to write geometric sequences as functions. So our first core concept. So when we're looking at this geometric sequence, the ratio between each pair is the same. So when we had arithmetic sequences, we had something like 2, 4, 6, 8, and each time I was adding the same thing. So in a geometric sequence, the difference here is I'm no longer adding something between my terms, I'm multiplying. And that thing that I'm multiplying by is called my common ratio. So this is something we're going to be using a lot. So we always find my common ratio, and that's the thing that I multiply by to get to the next term in my sequence. So here we're looking at example number 1. We have to decide whether each sequence is arithmetic, geometric, or neither, and then explain my reasoning. So I notice in part A to get from 120 to 60, I can either subtract 60, so let's try that, but then I see in the second part I can't subtract 60. That doesn't work. So I know that this is not an arithmetic sequence. Okay, so now let's try and figure out if it's geometric. So I see that to get from 120 to 60, I divide by 2. To get from 60 to 30, I divide by 2. Oh, and then I divide by 2 again. So the cool thing that this tells me is this ratio is the same, so this is geometric. And you might say, well, before we were multiplying by something. Well, dividing by 2 is the same thing as multiplying by 1/2. So I'm multiplying each of the terms by 1/2 to get to the next one. And so I'm still multiplying, so this is a geometric sequence. So now let's look at this one, part B. So I see to get from 2 to 6, I can either add 4, and we'll see if that works. So can I add 4 to this next part? Well, to get from 6 to 11, I have to add 5. So I know it's not arithmetic, so we can erase that. So now let's see if it's geometric. So to get from 2 to 6, I multiply by 3. Well, to get from 6 to 11, I can't multiply by 3. That doesn't work, so it's not geometric either. So I know that this second part is neither. And I did that by trying to add a common term, and then I tried to multiply a common term, and neither of those worked. So it is not geometric or arithmetic. It's neither one. Okay, so here is a monitoring progress. So go and try these and see if you can figure out what kind of sequence this is. So now we're going to look at extending our terms, right? Extending our sequence. So extending just means continuing it on. And this here is example number 2. I'm supposed to write the next 3 terms of each sequence. So the first thing I have to do is figure out what is happening to get to the next term. So I see to get from 3 to 6, and I know that these are geometric sequences, so I'm going to be multiplying. I multiply times 2. To get from 6 to 12, I multiply times 2, and I multiply times 2. So this I'm just double checking, make sure that I do have my sequence. So I know that to get to my next term, I would multiply by 2, so 24 times 2 is 48. And then to get to the next term, I would multiply by 2, which is 96. And then to get to the next term, I would multiply by 2 to get to 192. So you'll see if you're following along in your book, that these are written out in a table, which is a really easy, simple way to organize your thoughts and your sequences. So these are the next 3 terms in my sequence. Okay, so now let's look at the second sequence. Well, I see to get from 64 to negative 16, I might not know that off the top of my head, so in order to find that, I can take the second term, divide it by the first term. Well, that's a big number, and I could simplify it, so let's go a little bit further. I know if this is a geometric sequence, then the difference here will be the same as well, so I can take the third term and divide it by the second term. Well, this is something I can simplify, right? 4 goes into the numerator once, and 4 goes in the denominator 4 times. And this is negative. So this number right here is my common ratio. Right? This is the thing that's in between that I multiply by. Well, so I know that I just have to continue my sequence. So I take my negative 1 times negative 1/4, which gives me 1/4. Then if I multiply again, I'm going to end up with a negative 1/16. And then I multiply again and I become a positive 1/64. Not 1/64, 1/64. So I know that I can continue to multiply that out and continue my sequence. But here I'm just asked for the next 3 terms, so I can stop there. So now we're going to graph this one. Let me pull up a graph real fast. Okay, so now we're just going to graph the sequence now that we have our axes. And it may not pull up as high as we want it to. But I know that when my first term, when my x is 1, in this case my n, we're going to call these n's. Right? This is n sub 1, n sub 2, n sub 3. These numbers down here just tell me which term it is. So the first term is 32. So when my x is 1, we're going to count by 5s, and we're going to be pretty close, right? So 5, 10, 15, 20, 25, 30, 35. So it's a little bit less than 35. When my n was 2, it was 16. So 5, 10, 15, a little bit there. When n is 3, it's 8, 5, so a little bit there. And then when n is 4, we're 4. When n is 5 is 2. Do we see something that's similar? So I see kind of a curve that comes from when I graph my sequence. So along the line of what we've been looking at, this is an exponential curve. That's why we're talking about these geometric sequences right now, because we're dealing with exponential functions. So a geometric sequence models an exponential function. So here is another monitoring progress. So go ahead and think about this one and see where you can go from here. Okay, so we are going to look at some equations for geometric sequence. Before we really start there, I want to talk a little bit about more of the numbers. So in your book, you'll see on the top of page 334, we're writing geometric sequences as functions. Okay, so what I'm looking at is just some terminology here. And we can actually look at this core concept to get there. So a sub n be the nth term, right? And n just tells me which one. So whatever term I give of a geometric sequence with the first term a sub 1, right? And I see that sub 1 tells me the first term, and a common ratio r. The nth term is given by this equation. So a sub n tells me the number that I'm trying to get equals the first term, right? This is the first term, times the common ratio to the n minus 1, right? And this is my exponent. This is where our exponential comes into play. This is why we're talking about an exponential function, right? So again, just like any other exponential functions, right? We have a b to the x. It's kind of where I start, my first term, my common ratio, the thing that I multiply by every time, right? Which is my r, it might be here, and then my exponent. So the thing here is I just remember it has to be n minus 1. And it'll make sense when we get there, because if n is 1, right, your first term, that would make this exponent 0, which makes my r value 1, which leads us back to this first term. So I always have to have this n minus 1 in my exponent. Okay, so now let's look at an example. This is example number 4 in your book. We're going to be writing an equation for the nth term of this geometric sequence, 2, 12, 72, 4, 32, and then I have to find a sub 10. So the first thing I have to do is write my equation, right? And I know that a sub n equals a sub 1, my first term, times r to the n minus 1. So now I have to figure out the different pieces that I need. Well, I know that n is going to stay and a sub n is going to stay. So what can I automatically replace or substitute? Well, I know that a sub 1 is 2. That's my first term in my sequence that I'm given. So a sub 1 is 2. So now I have to figure out what my r value is. And to find my r, again, I figure out what do I multiply this term by to get to the next one. Well, I know to get from 2 to 12, I can multiply by 6. So my r becomes 6. So then I can just write the pieces of my function. This is the equation that models this geometric sequence, right? All I do is find the first term, I figure out my common difference, and then I plug in the pieces that I know. Well, so now I'm finding a sub 10. So again, I just take my function, 2 times 6, the n minus 1, right? Here's where my 10 goes. This is the piece where I'm told here. I'm told a sub 10 here, my 10 is here, and my 10 is here. So now I can go ahead and simplify that. So I end up with 2 times 6 to the 9th power. And I can go ahead and put this in my calculator, and I end up with 20,155,392. And remember, when I'm using this, when I'm using my calculator, I always want to do the exponent first. So I'm going to have 6 to the 9th equals, and then I can multiply that times 2 to get my final answer, right? So I always do the exponent first. So here's some more monitoring progress questions. Go ahead and try these. This is really help you see if you are right on track and know exactly where we're going before we continue to move on. So now we're going to be using our real world problems, and we're going to be modeling. This is example number 5. So when you click the zoom out button on a mapping website, doubles the side length of a square map. After how many clicks on the zoom out button is the side length of the map 640 miles? Okay, so the first thing I have to do is understand my problem. And I know that every time I'm doubling, right? So I know that this is an exponential equation because of the word double. So then I can write my function, right? And I know that I'm going to be dealing with geometric sequences, right? So I've got my function equals my a sub 1 times r to the n minus 1. This is going to be the format of my function, and I know that, so I can just continue with what I have there. So I see that my first term is 5, and my rate, I know, is going to be a 2 because I'm doubling every time. Okay, so all I've done is replace what I know into my function. So this represents that function. So now I'm trying to figure out when is that 640, right? So 640 is equal to 5 times 2 to the n minus 1. Well, man, this seems like big and complicated. Remember in our previous section, we were able to graph things. So let's go ahead and graph it. So what I've done here is you can see the two functions that I've graphed. I've created a system of equations, right, with my first equation and my second equation, and then I figure out where they're equal to each other. And using Desmos, I can just click on that dot, and it tells me that when my x value, or in this case n, is 8, that's when my f of n, or my y, is 640. So I know that the answer to this question, after how many clicks is the side length 640? Well, I know that my n is then equal to 8. It takes 8 clicks to get to 640 miles. So then I can also find this algebraically, right? Let's look at doing this algebraically. Because we looked at graphing, now we can do it just using our math. So I've got 640 equals 5 times 2 to the n minus 1. So the first thing I want to do when I have this and we're looking at mathematically, I want to divide by 5. So I end up with 128 equals 2 to the n minus 1. So now remember, when I have different bases, I want to try and find a similar base so that I can then set my exponents equal. Well, I know 2 can't get any more simple. So if I dig down deep and find that I can write 128 as 2 to the 7th equals 2 to the n minus 1. Well, now that my bases are the same, I can set my exponents equal. 7 equals n minus 1, and add 1 to both sides, so 8 equals n. And I see that I got the same answer here as I did by graphing it. So either way will solve the problem correctly and get me to where I want to be. So the next thing you'll see is just some monitoring progress to finish up this section. And so now is the time when you can go ahead and start working on your homework. But before we do that, let's take one last look at our learning targets. So our first one was identify geometric sequences. And we were able to do that here because we had to determine if it was geometric, arithmetic, or neither. And we know that it's geometric when I'm multiplying or dividing by the same number each time. My second learning target was extending and graphing geometric sequences. And I did that as well. When I extended them, I just found the next several terms of the sequence. Most of the time it'll ask you for 3, but sometimes it'll ask you for more. So you can just continue the work that we did if you need more problems, more questions, more parts of the sequence. And then we graphed it. And we noticed that whenever we graph a geometric sequence, we will end up with an exponential graph. And then thirdly, writing geometric sequences as functions. And that's what we did here at the end. We were given kind of the beginning of my sequence, and I had to write the equation of my sequence. But then again, I also did that when I had a word problem, right? I was just given the data here. So I know my first term was 5, my second term was 10, and my third term was 20. And with all of these things, I was able to find enough information to write my function. So now go ahead and open up your homework and get working on that.